All right, in this video, I'm going to be talking about permutations. So we define Sn to be the set of all bijections on the set of integers from 1 through n. Another word for bijection is permutation. So I'm going to be using permutation throughout instead of the word bijection, but you should understand that they mean the same thing. So Sn forms a group under the binary operation of function composition. Okay. So here I have the beginning of an example. So I've got two permutations, alpha and beta, in S7. And here I've written out what the permutations are using what I call a matrix notation for a permutation. So to understand how to read what I've written here, this is saying that alpha maps 1 to 4, alpha of 2 is equal to 1, alpha of 3 is equal to 7, and so on and so forth, okay? So remember, alpha being a permutation, it's a function. And as a permutation in S7, it's a function that which maps the numbers 1 to 7 to themselves. The fact that every number from 1 to 7 is listed down here shows that alpha is surjective, and the fact that there are no repeats here shows that alpha is injective. So hence alpha is a bijection or a permutation, okay? Similarly, we have the permutation beta down here, and so beta of 1 would be equal to 6, beta of 2 would be equal to 4, and so forth, okay? Let's do some examples of some computations with alpha and beta right now. So first, let's say I want to compute alpha times beta. Okay. Now remember that the group operation is function composition. So when I write alpha times beta, this is really alpha composed with beta, okay? Okay, so we can write out what alpha composed with beta is using this matrix notation again. Okay, so let's try to understand how this will work. So we first want to know what will alpha beta of 1 be equal to. So remember function composition, this is alpha of beta of 1, okay? So first, beta of 1 equals 6. So this is the same as alpha of 6, okay? So then we go up to here and we see that alpha of 6 is equal to 6. So hence, alpha beta of 1 we see is equal to 6, okay? Now I'm not going to write this out for everything, so I'm just going to do it a little bit more quickly, but hopefully you'll kind of get the idea as we go along. So to get alpha beta of 2, so first I would need beta of 2, which is 4. And then I would then need alpha of 4, which is 2. Okay. Let's see here. To get alpha beta of 3, so beta of 3 is 3. So then take that 3 and go up to here, and alpha of 3 is 7. Okay. Alpha beta of 4, so beta of 4 is 7. And then alpha maps 7 to 3. Okay. Alpha beta of 5, so 5 maps to 2. And then alpha will take that 2 and map it to 1. Alpha beta of 6, so beta maps 6 to 1, and alpha takes that 1 and maps it to 4. Okay. And finally, the only number that's missing is 5, so it must map 7 to 5. And we can check that just to confirm. So alpha beta of 7, 7 beta maps 7 to 5, and then alpha will map that 5 to 5 again, okay? All right. Let's just do a couple more examples of some computations like this. So we just did alpha times beta. So what if we want alpha squared? I can do that over here. Okay. So to get alpha squared, so alpha squared of 1. So first alpha maps 1 to 4. And then we're going to take alpha again. So we're going to take that 4 and alpha will map that 4 to 2. Okay. Now for alpha squared of 2, the first alpha maps 2 to 1, and then the second alpha maps 1 to 4. Okay. Alpha squared of 3, so the first alpha maps 3 to 7, and the second alpha maps 7 to 3. Okay. Alpha squared of 4, so alpha of 4 is 2, and then alpha of 2 is 1. Alpha squared of 5, so, all right, well, 5 is a fixed point, so alpha maps 5 back to itself. Okay. 6 is also a fixed point, so alpha will map 6 to 6, and then 6 to 6 again. Alpha squared is 7, so alpha of 7 is 3, and then alpha of 3 is 7. Okay. So that's alpha squared. Okay. Okay. What about beta inverse? So you might recall that every bijection is invertible. And of course, since we said the Sn is a group under function composition, so every element has an inverse. All right, so how would you find beta inverse? Well, remember the idea of the inverse is that it just maps everything like backwards, right? So all you need to do is read beta backwards, if you will, to figure out what beta inverse will be. So for instance, beta inverse would map 6 to 1. Beta inverse would map 4 to 2. It would map 3 to 3. 7 to 4. 2 to 5. 1 to 6. And 5 to 7. Okay, so that would be beta inverse. Let's say if we want beta to the power of -3. Okay, so this is beta inverse composed with itself 3 times. Okay, so let's see. So beta inverse maps 1 to 6. Okay, the next beta inverse would map the 6 to a 1. And then the third beta inverse would map the 1 to a 6. Okay. Okay. So then 2 would go to 5, and then to 7, and then to 4. 3 just keeps going back to itself. 4 would go to 2, then 2 would go to 5, and then 5 would go to 7. 5 goes to 7, and then 7 goes to 4, and then 4 goes to 2. Next, so the first beta inverse takes 6 to 1, The second one takes 1 to 6. The third one will take the 6 back to a 1. And then finally, 7 would map to 4, 4 would map to 2, and 2 would map to 5. Okay? All right. Let's just do one more. Since we've computed alpha squared and we've also computed beta to a power of -3. So let's say if we wanted, alpha squared times beta to the -3. Okay, so let's see here. So first, beta to the -3 is going to map 1 to 6. And then alpha squared will take that 6 and map it to 6. Okay. Next, beta to the -3 will map 2 to 4. And then alpha squared is going to take that 4 and map it to 1. Okay? So next, 3 would go to 3, and then that 3 would go to 3 again. Ugh. Okay. Let's see here. Beta to the -3 maps 4 to 7, and alpha squared takes that 7 and maps it to 7. So next, beta to the -3 maps 5 to 2, and alpha squared maps that 2 to 4. Next, beta to the -3 maps 6 to 1, and then alpha squared takes that 1 and maps it to 2. Lastly, beta to the -3, well, okay, so the only number missing is 5, so we kind of know it's going to map to 5 at the end. But just to confirm that, beta to the -3 maps 7 to 5, so alpha squared then takes that 5 and maps it to 5 again. Okay? All right, so those are just some examples of doing some computations with permutations using the matrix notation for them. A quick note, so S7 and Sn in general being a group, they should have an identity element. So just to be sure everyone knows what the identity element is, what is the identity permutation? The identity permutation is the permutation that maps every number back to itself. Okay? All right. Now, there's another way of notating permutations. So instead of this matrix notation that I'm using, there's also something that I call cycle notation. Okay? So I'm going to introduce how the cycle notation works. Okay. For the purposes of this abstract algebra class, probably the cycle notation, I would argue that's going to be much more important than the matrix notation. So you might like the matrix notation a lot, that's all right. But you got to make sure that you're familiar and comfortable with the cycle notation as well. So here I'm just going to illustrate with some examples. So I'm going to introduce another permutation in S7. And so this is gamma, and I'm going to write gamma like this. Okay, so what does this mean right now? Okay. So let me translate this back into matrix notation so that we can all kind of understand what this permutation gamma is doing. So the way you read this is gamma of 3 is 1, gamma of 1 is 4, gamma of 4 is 6, and gamma of 6 is 3. Okay? That's what that cycle notation is telling us. Now, as for the numbers 2, 5, and 7, which were not listed in here, any number that is not listed in the cycle notation is assumed to map to itself, meaning gamma of 2 would be 2, gamma of 5 would be 5, and gamma of 7 would be 7. Okay? All right, so I want to do some computations with cycles now, so we can get a feeling for how that will work. The first thing that I want to do is I want to compute some powers of gamma. And I'm going to be writing all of my answers as cycles, as opposed to using the matrix notation. Okay. So how do we figure out what gamma squared will be? Well, so gamma will first map, okay. Well, so gamma squared, just again, remember that's gamma composed with gamma. Okay. So let's see. We know that gamma of 3 is 1, and then the second gamma will take that 1 to a 4. So if I gamma squared of 3 should ultimately map to 4. Okay. So next, what is gamma squared of 4? Okay. Well, the first gamma maps 4 to 6, and the second gamma will map the 6 to 3. So to indicate that 4 maps to 3, I would want to close this cycle. Okay. All right, so I have the numbers 3 and 4. I'm missing the numbers 1 and 6, so let's take the number 1 next. So gamma squared of 1. So the first gamma maps 1 to 6. The second gamma maps, the first gamma maps 1 to 4. And the second gamma maps 4 to 6. So that 1 ultimately maps to 6. And then you can kind of figure out that 6 will have to map back to 1, since that's the only number remaining, but just to kind of confirm. So the first gamma maps 6 to 3, and then the second gamma maps 3 to 1, okay? So to compute gamma squared, what's happening? Essentially, you just need to move over twice every time, okay? So gamma squared of 3 was 4, right? Gamma squared of 4 was 3, and so forth, okay? Right. Now, as for gamma squared of 2, we know that gamma always maps 2 to 2, and 5 to 5, and 7 to 7. So I don't need to write anything for that. The fact that 2, 5, and 7 are absent just indicates that they map to themselves again, okay? All right, so let's do gamma cubed. So for gamma squared, we had to move everything over twice. So for gamma cubed, we're going to move everything over 3 times. So gamma cubed of 3 is going to be 1, 2, okay. Gamma cubed of 3 is 6. So what is gamma cubed of 6? So 6 will go to 3, then 1, then 4. Okay. Gamma cubed of 4, so 4 goes to 6, then 3, then 1. And gamma cubed of 1 will go to 4, then 6, and then back to 3, okay? So since 1 goes back to 3, I close the cycle. And then just again, 2, 5, and 7 are just going to keep mapping back to themselves. and I don't need to write anything to indicate that. Okay. So lastly, what is gamma to a power of 4? Okay. So that means I'd be moving everything over 4 times. So like gamma to the 4th power of 3, so 3 will go to 1, then 4, then 6, and then back to 3. So in other words, 3 maps to itself. Okay. Now you could just write it as that to indicate that 3 maps to itself. But as I've been saying with 2, 5, and 7, if a number maps to itself, you don't need to write anything for that. Okay. Now if you continue though, gamma to the 4th power will map 1 to 4, 6, 3, so ultimately to 1. Since 1 maps to itself, I don't need to write anything for that either. 4 will also map to itself, and likewise 6 will map to itself, okay? So gamma to the 4th power maps every number to itself. That means that gamma to the 4th power is the identity permutation, okay? So it's not a coincidence that gamma was a cycle of length 4. And when I say that gamma is a cycle of length 4, I just mean that there's 4 numbers in the cycle. So it's not a coincidence that gamma is a cycle of length 4, and that gamma to the 4th power gives you the identity. So one important fact about cycles is that the order of a cycle, remember the order of an element of a group was the smallest positive integer, for which raising to that power will give you the identity element, okay? So the order of a cycle is its length. Okay? So every cycle of length 4 is going to be a permutation of order 4, meaning that 4 would be the smallest positive integer that you need to raise the cycle to that power to get the identity permutation. Okay? And that is a very important fact. Now, I want to make a couple other comments about cycle notation and do just some other examples of some computations. One thing that's kind of interesting to note about cycle permutation okay, so gamma, I wrote it as a cycle 3146. Now, if I shift all the numbers in the cycle over to the left, so like if I write 1 first, and then 4, and then 6, and then 3 shifting left would put it at the end here. Yeah. So I want you guys to observe that these are actually the same thing. Okay. So why is it that they are the same? Well, both of them say that 1 maps to 4. Both of them say that 4 maps to 6. Both of them will say that 6 maps to 3. And both of them say that 3 maps to 1. Okay. And since 2, 5, and 7 are missing, both of them say that 2, 5, and 7 map to themselves. Okay. Okay. And then again, you can keep shifting the numbers over by one spot, and you'd get the same permutation. Okay. So that's one thing to note, is that cycle notation is not unique. You can express the same cycle in like a couple of different ways. So that's one thing to note about cycles. Let me do another example right now of just multiplying 2 cycles together. So let's say I have the cycle 2, 3, 5, 1. I'm going to multiply or compose that with the cycle 1, 4, 2. And then let's say that's also composed with, let's do maybe 7, 3, 5, okay? All right, let's give these guys a name. So let's call this one delta 1. We'll call this one delta 2. Let me call this cycle delta 3. So I want to express the composition or the product of these three permutations. And I want to express it in terms of cycles. So how would I do that? Okay. So what you can do is pick any number. And so I'm still working in S7, okay? So let's pick any integer between 1 and 7. It doesn't matter which integer that you choose, okay? But it's kind of natural to start with the number 1, so that's what I'm going to go with. Okay. So I need to know what is 1 going to map to. So remember how this works. I want to do delta 3 of 1 first. So delta 3 of 1 would be equal to 1, since 1 was not listed in the cycle, okay? So delta of 3 is 1. So next we need delta 2 of 1, okay? Now delta 2 of 1 is 4. So then we now need delta 1 of 4, okay? And since 4 is not listed in the cycle for delta 1, that means that 4 maps to itself. So delta 1 of 4 is 4. So ultimately, this product or this composition maps 1 to 4, okay? So to do that a bit more quickly, okay, so 1 maps to 1, then that 1 maps to a 4, and then that 4 maps back to 4, okay? Let's do the rest of it more quickly now. So I need to now see what will 4 map to. So 4 maps to 4 first, then the 4 maps to a 2, and then that 2 maps to a 3. Okay, now 3, what does 3 map to? So first, 3 will map to a 5. The 5 will map back to 5 here, and then that 5 will map to a 1 over here. So starting at 3, we went back to 1, so I want to close the cycle to indicate that 3 maps to 1, okay? Now so far I only have the numbers 1, 4, and 3 accounted for. So if I want to know what's happening to the other numbers that are missing, what we'll do now is just take one of the numbers that are missing. Again, it doesn't matter which one you take. I guess the first number that's missing though is 2, so let's go with that. So let's see what happens to 2. What does 2 get mapped to? So first, delta 3 will map 2 to 2. Then delta 2 will map that 2 to a 1. And then delta of 1 is going to take that 1 and map it to a 2. Okay, so 2 maps to itself, okay? Now, again, I don't need to write this down though. I can just leave the 2 off, and it will just be implied that 2 maps to itself, okay? I'm going to leave this here for now. There's nothing wrong with that. But at the end, I think I'm going to simplify just by removing it, okay? All right, so let's see. We have the numbers 1, 2, 3, 4. Let's take the number 5, which is missing right now, and let's see what happens to 5. So delta 3 maps 5 to 7. Delta 2 will map the 7 back to 7. And then delta 1 will map the 7 back to 7 again. So 5 will go to 7. Delta 3 of 7 is 3. Delta 2 takes that 3 and maps it to 3. And then delta 1 will take that 3 and map it to 5. So to indicate that 7 goes to 5, I would close that cycle. So now the only number that I'm missing is 6. So 6 would have to be in the cycle by itself. But if we just want to confirm that real quickly, no, delta 3 of 6 is 6. Delta 2 takes that 6 and maps it back to 6. And then delta of 1 will take that 6 and again map it back to 6, okay? And I can drop the 1 cycles that I have here, the cycles of length 1, and more simply write it like this. Okay. And then the fact that 2 and 6 are missing tells us that 2 maps to 2 and 6 maps to 6, okay? All right, so there's just a little example of how to multiply cycles together. All right. So here, when I first introduced this cycle notation, so we saw how to convert from cycle notation to matrix notation. So if we want to go from matrix notation to cycle notation, how do we do that? So it's actually pretty simple. I'm going to illustrate with the permutations alpha and beta that I had up here. So we have alpha and beta written in matrix notation. And I'm going to rewrite them now in terms of cycles. Okay. So here's how we do that. So it's kind of similar to how we did this multiplication actually. So I'm going to pick any integer between 1 and 7. It doesn't matter which integer that I choose, but it's natural to start with the number 1, so I'm going to start with 1. Okay. So let's see, alpha maps 1 to 4, so 1 maps to 4. Alpha maps 4 to 2, so 4 maps to 2. And then alpha maps 2 to 1, so to say that 2 goes to 1, I'm going to close the cycle. So next, take a number that's missing right now. I'm missing the number 3, so let's start with 3. Alpha maps 3 to 7, so 3 maps to 7. And then it maps 7 to 3. So to say that 7 goes to 3, I want to close the cycle. Okay. Now 5 and 6 map to themselves. So you could write 5 and 6 by themselves in like a cycle of length 1. But as I've said a couple of times already, if a number maps to itself, you don't need to do anything for that at all. Okay. So then this would be alpha in terms of cycles. Let's just do the same thing for beta real quickly. So take any integer from 1 to 7. Again, I'll just start with 1. So beta maps 1 to 6. It maps 6 to 1. So I'll close the cycle since 6 maps back to 1. So let's take another number that's missing. So let's take the number 2. 2 maps to 4. 4 maps to 7, 7 maps to 5, 5 maps to 2. So to say that 5 maps to 2, I will just close the cycle. And then the only number that's missing here is 3, and 3 maps to itself. So I don't need to write anything for that. The fact that 3 is missing would indicate already that 3 maps to itself, okay? All right, so that's how you can convert from matrix notation to cycles. Now, something that is very important to note about these two examples. So we factored alpha and beta into a product or composition of cycles. Also note that these cycles in each of the factorizations, these cycles are disjoint, okay? Meaning that there's no number that appears in multiple cycles, okay? Every number appears exactly once in a cycle, or it doesn't appear at all, meaning that it maps to itself, okay? So this procedure of taking a permutation and writing it in terms of cycles, this procedure that I did in these two examples, you can apply this procedure to any permutation. And what that will lead to is a factorization of your permutation into disjoint cycles. Okay? So any permutation can be factored into a product of disjoint cycles. Okay? Just do what I did in these two examples to any other permutation, and you will factor it into a product of disjoint cycles, okay? Now, this factorization is essentially unique, okay? Okay, so what do I mean by essentially unique? So remember how I talked about that you can write a cycle in different ways? So like this cycle 1, 4, 2 is the same as the cycle 4, 2, 1. Okay. It's like here's another way of writing alpha as a product of disjoint cycles. But it's not really different because these two cycles are actually the same. Okay. Likewise, you could include these cycles of length 1 if you really wanted to. Okay. But we don't really consider that as really different, if you will, from what we have right now. So aside from these sort of like cosmetic changes, if you will, the factorization is essentially unique, okay? Now, so why is this important? So first, let me talk about why it's kind of important that cycles are disjoint, okay? So what's the benefit of having disjoint cycles? Um, let me point out something to you guys. So let me take alpha right now. So alpha was the product of the cycles 1, 4, 2, and 3, 7. Okay. Now, what if I reverse the order of that and I do 3, 7 multiplied or composed with 1, 4, 2? And I think just to make it super explicit, I'm going to convert this to matrix notation to see what's going on, okay? So let's see, 1, the first 1 will map to 4, and then that 4 will map to itself. So 1 will map to 4, okay? Let's see here, 2 maps to 1, and then 1 maps to itself. 3, the first 3 maps to 3, and then that 3 will map to 7. 4 will map to 2, and then that 2 will map back to 2. Starting at 5, 5 will map to 5, and then that 5 will map to 5 again. So we end at 5. Starting at 6, so 6 will map to 6 first, and then that 6 will map to 6 again. And finally, starting at 7, 7 will map to 7, and then that 7 will map to 3, so we ended at 3, okay? And notice that this is exactly the same as what we have up here for alpha, okay? So 142 times 37 was actually the same as 37 times 142. So the takeaway from this example is that in general, disjoint cycles commute. Okay. So this is like A times B equals B times A. So remember that property was known as the commutative property. So disjoint cycles commute, okay? If your cycles are not disjoint, they will not commute. Okay? So that's kind of important to note. Now, this disjoint factorization one of the main uses of the disjoint cycle factorization is that it allows us to easily find the order of any permutation. Okay? And so I'm going to try to explain how this works. Now, we've already seen that for a cycle, let me scroll up real quickly. So we've already noted that the order of a cycle is its length, okay? All right, so let me continue using alpha right now as an example. So we have alpha as a product of a cycle of length 3. I'm going to call that alpha 1. And then times or composed with a cycle of length 2, which is 3, 7. And I'm going to call that one alpha 2. So since alpha 1 is a cycle of length 3, I know that alpha 1 cubed is the identity. Likewise, since alpha 2 is a cycle of length 2, that means that alpha 2 squared will give me the identity permutation, okay? So then in general, any alpha 1 raised to any power that is a multiple of 3 will be the identity. So that's if and only if. M is a multiple of 3. And likewise, alpha 2 to a power will be the identity, only if that exponent was a multiple of 2. Okay. So I'm interested in finding the order of alpha right now. So what do I need to raise alpha to a power to in order to get the identity permutation? So let's compute alpha squared right now. And I'm going to compute alpha squared symbolically. Okay, so not using these numbers, but just using the fact that alpha was alpha 1 times alpha 2. So alpha is alpha 1 times alpha 2, and then alpha squared should be alpha times itself. Okay? Okay, so that would be alpha squared right now. Now here, the fact that alpha 1 and alpha 2 are disjoint means that they commute, right? So we talked about how disjoint cycles commute earlier. So because alpha 1 and alpha 2 commute, I can interchange the order of the 2 in the middle and say that this is equal to alpha 1 times alpha 1 times alpha 2 times alpha 2. Or in other words, alpha squared turns out to be alpha 1 squared times alpha 2 squared. Okay? So you can generalize this, and you'll find that alpha to the power of m would equal alpha 1 to the m times alpha 2 to the m. Okay? But I want to stress that this only works because I know that these cycles are disjoint and therefore they commute. Okay. Now here's going to be the idea of finding the order of alpha. Basically, for alpha to the power of m to be the identity permutation. Okay, well, alpha to the m is alpha 1 to the m and alpha 2 to the m, right? So for this product to be equal to the identity permutation, so I'm not going to go into this much, but because they were disjoint cycles, the only way for this to happen is for alpha 1 to the m to have been an identity, as well as alpha 2 to the m to be identity. So you can kind of see how that works. If these are both equal to the identity, well, identity times identity should just give you the identity again, okay? All right. So what is the smallest number for which alpha 1 to the m will be the identity and for which alpha 2 to the m will be the identity as well? Well, for this first condition to be satisfied, m would have to be a multiple of 3 because alpha 1 was a cycle of length 3. And for this condition to be satisfied, m would have to be a multiple of 2 since alpha 2 was a multiple of 2. So I need m to be both a multiple of 3 and a multiple of 2. So the smallest number satisfying that would be m equals 6, the least common multiple of 3 and 2. Okay. So with that kind of reasoning, we can conclude that the order of alpha is 6. So 6 is the smallest positive integer that I would need to raise alpha to a power 2 to get the identity permutation. And we figured that out without computing all the powers of alpha to get alpha to the 6th. Okay? So in general, you can find the order of a permutation sigma by doing two things. So first, you want to find the factorization into disjoint cycles. Once you have the factorization into a product of disjoint cycles, the order of sigma will be equal to the least common multiple of the lengths of the cycles in the disjoint factorization. So that's exactly how this example worked in kind of explaining the order of alpha is 6. Ultimately, it turned out to be 6 because 6 was the least common multiple of 3 and 2, where 3 and 2 were the lengths of the cycles in the disjoint factorization of alpha. Okay? So then just like as another quick example of this, I'm just going to make something up. So let's say sigma was a permutation in S, maybe 13. And let's say that you found the disjoint factorization of sigma already. And its disjoint factorization was maybe 1, 8, 3, 2, 10, 7, 5, and maybe 12, 6. Okay? Okay, so we have this permutation, we factored it into a product of disjoint cycles. So what is the order of this permutation in S13? Well, the order should be the least common multiple of the lengths of each of these cycles. So the lengths are length 3, 4, and 2. So then what's the least common multiple of 3, 4, and 2? That would be 12. Okay? So without having to raise sigma to any power, I can already tell that sigma to the 12th power will be the identity permutation, and that 12 is the smallest such positive number that would do so. Okay? All right. Lastly, I want to talk a little bit about transpositions. So a transposition is a cycle of length 2. Okay? All right, so it is a fact that every permutation can be factored into a product of transpositions. So let me illustrate how that would work. So we know that every permutation factors into a product of disjoint cycles. So if we can just factor every cycle as a product of transpositions, we could then easily factor any permutation into a product of transpositions. So let me take, earlier we had this cycle in S7. Gamma was 3, 1, 4, 6. So we can factor this cycle as a product of the transpositions 3, 1, 1, 4, and 4, 6. Okay? So 3, 1, 1, 4, and 4, 6. Okay? Now let's confirm that these are actually equal to each other. Okay? So 3 should map to 1. Let's confirm that's the case on the right-hand side. So 3 will first map to 3. Then the 3 will map to 3 again. And then the 3 will map to a 1 in the end. Okay? Now 1 should map to 4, so let's check that. 1 will first map to 1, and then the 1 will map to a 4, and then the 4 will remain at 4. So 1 ultimately maps to 4, okay? 4 should map to 6, so 4 maps to 6 here, and then the 6 will remain at 6, and then over here it will remain at 6 again. So 4 will ultimately map to 6. Finally, 6 should map to 3. So over here we have 6 would map to 4, that 4 would map to a 1, and then that 1 does ultimately map back to 3. Okay? So that's how you can confirm that both sides are in fact equal to each other. And you can do this for any cycle to factor it into a product of transpositions. So now let me take this example of this permutation sigma, which we have written as a product of cycles. So to express it as a product of transpositions, well, using the same idea of this example, 183 should factor as 18 times 83. This cycle should factor as 2, 10, 10, 7, and 7, 5. And then 12, 6 is already a transposition, so I don't need to do anything to it. So then here we have sigma factored as a product of transpositions. Okay? So in general, to factor a permutation into a product of transpositions, you can just factor it into disjoint cycles first, and then factor each of those cycles into transpositions. Okay. Now, this is not the only way of factoring a cycle into transpositions, although I think it's kind of the easiest way of doing so, personally. So the factorization into transpositions is not unique in the way that the factorization of disjoint cycles was. Okay? Now, although the factorization into transpositions is not unique, there is something that you can say about the factorization still, okay? So every factorization of a permutation into a product of transpositions will have either an even number of transpositions in it, or an odd number. Okay, so if you take a permutation, then no matter how you factor it into a product of transpositions, it will either always end up with an even number of transpositions in it, or every factorization will always end up with an odd number of transpositions in it, okay? So then we define a permutation to be an even permutation. If it factors as an even number of transpositions, so as a product of an even number of transpositions. And likewise, a permutation would be odd if it factors into an odd number of transpositions, okay? And then just to kind of make sure I'm being clear, you'll never have a permutation that factors into both an even number of transpositions and also an odd number of transpositions. So either every factorization gives you an even number, or every factorization will give you an odd number, okay? All right. So then, like for example up here, this permutation factored into a product of 6 transpositions. So sigma would be an even permutation. Every other factorization of this permutation sigma into a product of transpositions will have an even number of transpositions in it, and you would never find a factorization of sigma into a product of an odd number of transpositions, okay? Okay, so with that, let me just end with a couple of miscellaneous comments, all right? So an even permutation multiplied or composed with another even permutation results in an even permutation. An even permutation composed with an odd permutation results in an odd permutation. And two odd permutations composed or multiplied with each other results in an even permutation. Okay. You can think about why that's the case. It's not that difficult to figure out. The fact that two even permutations composed with each other gives you another even permutation. That means that the set of all even permutations in Sn is closed under the group operation of function composition. So in fact, the set of all even permutations forms a subgroup of Sn, okay? So people use AN to denote the subgroup of all the even permutations. In Sn, okay? And then just a couple other miscellaneous facts that I wanted to mention, and then I'm going to wrap up the video. So the number of permutations in Sn, so the number of elements in Sn, the order of the group Sn, is equal to n factorial. So it's sometimes good to know that. Half of these permutations are even permutations, and the other half are odd permutations, okay? So the order of AN, which would be the number of even permutations in Sn, as I said, it would be half of n factorial. And then the other half of the permutations are all odd, okay? And then finally, I've kind of hinted at it when I was talking about how disjoint cycles commute, but cycles which are not disjoint do not commute. It's also worth noting that Sn is not abelian. When n is greater than or equal to 3, okay? So this gives us sort of a class of non-abelian groups, because up until this point, you've almost always been working with abelian groups. But not all groups are abelian, so it is useful to have some examples of non-abelian groups on hand, and Sn for n greater than or equal to 3 gives you one such class of non-abelian groups, okay? That is all for this video, so thank you for watching.